So this is the point in our study of algebra at which things kind of take a turn a little bit, where the kinds of expressions and the kinds of equations that we're going to start working with are going to be more complex. They're going to be complicated in a way that we're not used to yet. And that's because today is the day that we introduce exponents. If you'll remember, when we first talked about the order of operations, we kind of situated the order of operations in such a way as to highlight how the operations of arithmetic are built out of one another. Right? That we have addition and subtraction, which in a sense are the simplest operations that there are in arithmetic. But then on top of addition is built the operation of multiplication. Right? To multiply something is to add it to itself repeatedly. So 3 times 4 is just another way of saying 3 added to itself, with a total of 4 terms. And so multiplication and division, its opposite, are kind of more complicated operations than addition and subtraction were. And because they're higher order operations, they come first in the order of operations. They come before addition and subtraction do. So of course then the next logical place for us to go is one step higher, and to look at the operation which is built out of multiplication, which we call the operation of taking an exponent. So if I take, for example, let me just move this out of the way for a moment. If I take, for example, the expression 3 to the 4th power, what does that really mean?
3 times 3 times 3 times 3.
Right. So in the same way that multiplication is built out of a repetition of addition, 3 to the 4th power means we're going to use repetition of multiplication to build a power. Right? So I multiply 3 by itself 4 times. 3 times 3 is 9, times 3 is 27, times 3 is 81. And so that's the next sort of evolutionary step in our understanding of arithmetic, is to look at the repetition of multiplication. Right? Multiplication, repeated multiplication of a number is the same as raising that number to a power. And so the expressions that we deal with from here out are going to be expressions that may involve powers. So far, everything in the first 3 chapters of this text dealt only with these bottom operations. So expressions and equations that involve only multiplication, division, addition, and subtraction, we'll call those linear expressions or linear equations. And so that's what we've done up until this point. But now that we're also adding exponents into the mix, we can start to build what we might call nonlinear behavior. Nonlinear expressions, nonlinear equations. So stuff that can happen that kind of doesn't always follow the same rules as the expressions that we worked with up until this point. So our first goal in dealing with this new type of expression is to sort of pop the hood a little bit, get to know them, get to know their anatomy. What kinds of expressions are we talking about? And we're going to talk about today about polynomials. And what are polynomials? What do they mean? What features do they have? And then to begin to get into the topic of how to do arithmetic with those expressions. So how to add them together and how to subtract them from one another. What does the word polynomial look like it means? Let's say I split it up into 2. I have a poly and I have a nomial. Okay, so what are we seeing here in the first part of it? What does poly indicate? Many, right? Many or several. So that's for poly. Okay. The poly part means many. Nomials. Yeah. So let's say many numbers. Nomials, the nom root for this sometimes also means names. So we could think in addition of numbers also things that have the names of numbers, say variables, right? So these are going to be expressions, and if we want to get a completely specific definition of what a polynomial is, what we'll say is first, before we can understand what a polynomial is, let's take a moment and understand what happens if we replace poly, for many, with mono, for one. So let's talk about what is a monomial. So a monomial is, first of all, an algebraic expression. It's an expression that has only a single term. So remember we talked about terms and factors before. So here I'm using the word term very specifically. Right. So it's an expression that has only one term. And we have one more stipulation for what makes a monomial. And it's that the variable that appears in this term any variable that appears in this term has to have a whole number exponent. So I'm trying to be real specific here about what's going to count as a monomial and what's not. Whole number exponents. So give me an example of something which would be a monomial. Three to the fourth. Sure. That's a monomial. It's an expression that only has a single term in it, and every variable which appears has only a whole number exponent. Well, there are no variables, so that part of it doesn't even matter. But 3 to the 4th certainly qualifies. What's an example of a monomial that would have a variable in it? Yeah. 2x. Sure. That's a monomial because it's an expression that has only one term, and the variable x has a whole number exponent. What is the exponent on that x right there? Yeah, it's the secret hidden exponent of 1, x to the first power, right? Right, so 2x is a monomial. Give me one more example of a monomial that might have a different exponent besides 1. 3x squared. Sure. That's a monomial. Okay. It's an expression with only a single term in it, and the variable, which in this example is x, has an exponent which is a whole number, specifically 2. So all of those are examples of monomials. All right, so what's an example of something which is not a monomial? Maybe that's the next place to go with this. What would not a monomial look like? There are two places that we could kind of attack this definition. We could attack the one term part of this definition, or we could attack the whole number exponents part of this definition. So let's suppose I wanted an example of an expression which has whole number exponents but which doesn't have one term. What would an example look like? Okay, so here's an example of an expression which has two terms in it, right? Because it's got two bits that are added together. They're not like terms, so there's nothing I can do to combine them together and make this expression any simpler than it is right here. And so because it has two terms, that doesn't qualify it as a monomial, right? A monomial is something that has only one term. But what can you tell me about the exponents in each of the terms here? 3x, what's the exponent there? 1. The second term here, 3 by itself, has no x term in it. So the exponent is 0. So that's also a whole number. So there's something that's nice about this expression. Even though it's not a monomial, each one of its terms is a monomial. So 3x is a monomial, and 3 is a monomial. But when we add them together, we get something which is not a monomial. And as you might suspect, what it is it's a polynomial. Right? Okay. Can you think of another example of something which is not a monomial, but which does have one term? What might that look like?
Could it be like 2x to the like 2.5?
All right, sure. So here's an example of an expression which is not a monomial. We're not going to call it a monomial. Because even though it has one term, right, because it's not a bunch of stuff added together, it has only one term, the exponent on the variable is not a whole number. So 2x to the 2.5 is not going to qualify as a monomial for our purposes. This one kind of breaks a lot of the rules. Because even if we knew what x was, it's not immediately clear to us how we could raise x to the power 2.5. We know how to square a number, multiply it by itself once. We know how to cube a number, multiply it by itself with 3 factors inside of it. But how do you multiply something by itself 2.5 times? Right. So that's why we're not going to talk yet about expressions in which the exponents are not whole numbers. Right? So that doesn't qualify. This doesn't qualify. But 3x plus 3 is somehow a lot friendlier still than 2 times x to the 2.5. And so what we'll do is that we will take an expression like 3x plus 3, and even though it's not a monomial, we will qualify it as a polynomial. So a polynomial is nothing more than a sum of monomials. A sum or a difference.
So 3x plus 3 is a polynomial.
It is a polynomial, yes. It's not a monomial because it has 2 terms. But because each of those terms is a monomial, that makes 3x plus 3 a polynomial.